longer shot considering. Couldn't get enough speed. So the power hitter misses the fairway, settles for par at 6.
Right back here at 8, Billy Horschel will tap in for his double bogey. So drops back to 6 under. Thomas ready to play his second. 169 compared normally. I think he hit us with the green.
Okay, guys, welcome back.
Make it tough to not hit that. That's exactly what he did. But in the fairway, that's huge there third. Yeah, John, we've seen 3 players now play out of the fairway bunkers down this 8th hole. Not one has been able to hit the green.
Yeah, that makes it harder to bail.
Welcome back.
Yeah, you almost say, I gotta put this in the fairway.
Exactly. You're almost better to miss the bunkers. Bunker is prepared here, Paul. See how the rings are perpendicular to the hole. They're not running in the direction of the hole. So great point. Easy to get that.
Okay.
Sand behind the ball.
So to continue,
Ace man from yesterday.
a vector has a starting point
In there.
and a terminating point. So here we represent this vector starting at O, terminating at A by a line and an arrow designating the direction. The length is the magnitude of the vector, and the arrow indicates the direction.
Jordan Speed, taking his time over this one.
This vector starting at O, ending at A, is denoted as OA, and a line over it indicating that it's a vector.
So right to the hole here, if you could get it up into the center of the green, that'd be great. You got that right. Anything left is a nightmare, and that's not left.
So
up to the right bunker, and that's a similar length of
vector R
see if you can do better.
is OA.
Hard shot. Just off the other side of the fairway rush. Yeah, 232 up this hill.
The magnitude of the vector is denoted as such. Vector OA with these 2 lines. So you denote a vector by both lines, OA, and the magnitude R.
Yeah, take a look at the route.
Now, a very important concept
This is a shot that Paul, I watched him warm up this morning. He must have hit
in our numerical system. We count. In our numerical system, we count by 1. Or in base 10, we count by 1. So to count, so 10 or 4 is 1 plus 1 plus 1. That is 4. Now in vector, we have units of the given vector. We call the unit vector. So a vector R hello? I'm here. No, I'm not scheduled for non-lab. Which class this? No, I teach electromagnetics now. But did you come to class? Yeah, but remember I said the labs are simulations. So I will send the labs them to you guys. And you do it in your own time. Okay. Thus, for any vector to indicate the direction, a unit vector can be used. Consider the unit vector OA. So unit vector A in the OA direction is one unit of this vector OA. So for that particular vector R, unit vector OA is one unit of the vector in the direction OA. So in the same way, when you count, the unit is one, the unit vector along OA is one. In other words, four is 4 units of one. Vector OA is R units of OA. So vector OA is R OA. So we represent OA by little a with the vector sign over it. So this is the unit vector. AX, or little ax, is a unit vector along the x-axis or x direction. Similarly, that's in Cartesian coordinate. Oh my God. Hello? There I'm on. I'm with that class. Yeah? Tomorrow. Oh, you want something? Okay. I don't know, I'm gonna check. Oh yeah. No, I don't want to. All right, cool. All right, cool. All right, cool. Okay. Right. Is that me? Tomorrow. Okay. So AX would be the unit vector in the x direction. Now, we have various mathematical operations. For example, we can add two numbers. We can scale a length. We can subtract. We can do the same thing with vectors. Now, let alpha equal a scalar with which a vector is multiplied. Let alpha be greater than 1. Then the magnitude of the vector increases, but direction remains the same. This is shown in 1-3. So here we have a vector A. If alpha is greater than 1, alpha A is alpha multiplied by the vector. So we can scale the magnitude, but not the direction. If alpha is less than 1, say half, then the same thing occurs. If alpha is negative, the magnitude remains the same. but the direction is reverse. Of course, you can have alpha minus equal minus a half. It would still change direction, but the magnitude will split in half. How do you add two vectors together? Now, here you have vector A in this direction. And you have vector B in this direction. A plus B. You complete the parallelogram, and A plus B will be equal to C, as seen here. So, just like A and B, the direction of C is from O. Okay. Now, like numbers, vector A plus vector B is the same thing like 2 plus 3 equal 5, 3 plus 2 equal 5. It's called a commutative law. Vectors obey the commutative law. So vector A plus vector B is equal to vector B plus vector A. Okay. So here is the parallelogram rule. You complete the parallelogram. That means you're drawing a side here, which is equal in magnitude to this. And you're drawing a side here, which is equal in magnitude to this. Complete the parallelogram. Draw your vector C from the origin to this corner. So, vectors obeys the commutative rule. You can add or subtract any amount of vectors. That means you can add vector A plus vector B plus vector C plus vector D to give you a resultant vector. And again, we're talking here about the rectangular coordinate system, but it could be any system. It could be the cylindrical system, as well as it could be the spherical system. The rules still apply. I'm gonna turn this off now. I can't. Too much interruption. I leave it on because some students still don't know and they keep calling, but I'm getting distracted now. Hello? Yeah, in class right now. I can't talk to you right now. I'll call you back. Okay. So here we have 4 vectors. A, B, C, and D. So we are going to add A plus B plus C plus D. A plus B plus C plus D. So we get a resultant here, which is the sum of the 4 vectors. So again, we have these 3 basic laws of algebra that the vector also apply, or they also apply to the vector. Again, the commutative, vector A plus vector B is equal to vector B plus vector A. Vector A plus vector B plus vector C is the same thing as vector A plus B plus vector C. We call this the associative law. The distributive law, alpha times vector A plus vector B is alpha times vector A plus alpha times vector B. For multiplication by a scalar, alpha times vector A is the same thing as vector A times alpha. For two scalar, beta times alpha A is the same thing as beta times alpha times A. And for the distributive, alpha plus beta times vector A is alpha times vector A times beta times vector A. So for the commutative, the associative, and the distributive laws of algebra, it also, for addition and multiplication, it also holds for vectors. Now let us look at subtraction. As you know, 5 minus 2 is the same thing as 5 plus negative 2. This also applies to vectors. Vector A, you have two vectors here, A and B. Vector A minus vector B is the same thing as vector A plus negative or minus vector B. So you have vector A here, vector B here. Negative vector B is this. Same magnitude as B in the opposite direction. So vector C, which is A minus vector B, would be this. Two vectors are said to be identical if their difference is 0. Thus, A and B are identical if vector A minus B equals 0. So let me restart here. Okay. I mentioned this before. You're most familiar with the Cartesian or rectangular coordinate system. That's X, Y, and Z. I said earlier, there are other Cartesian, there are other coordinate systems. And we will be treating, or we will be dealing with electromagnetics problems in these three systems: Cartesian, the cylindrical, and the spherical systems. So let us look at these three systems in some more detail. So this is also called the rectangular coordinate system. So this system has three coordinates: X, Y, and Z. And they are they are at right angles to each other. And these three axes intersect at a common point called the origin. So here is your rectangular coordinate system. We have what we call the right-handed system, where you have X, Y, and Z. So you rotate X into Y. The left-handed system, you have X, Y, and Z. Rotate X into Y. In left-handed system, X and Y, as you see, axes are interchanged compared to right-handed system. This means the rotation of X-axis into Y-axis through smaller angles cause the downward movement of the right-handed screw in the Z direction. For the most part, we are going to be using the right-handed system. Now, when we say the X, okay. Look at the rectangle. You have this side, we call it a plane. You have this side, you call it a plane. You have this side, that's a plane. You have one back here, that's a plane. You have one here, that's a plane. And we have one here. That's a plane. If we say the x equal 0 plane, that is a plane at x equals 0. That means it would be this plane back here. The z equals 0 plane would be this plane. The y equals 0 plane would be this. So if we say a sheet of charge lies in the x equals 0 plane, you know, the sheet of charge lies here. Of course, we can say a sheet of charge lies in the x equal, say, 7 plane, and therefore this would be 7, and it would lie in this plane. And the same goes true for the y and the z coordinates. Okay. So x equals 0 plane would be the plane at x equals 0. And the plane have the dimension y and z. The y equals 0 plane would have dimension x and z at y equals 0. And the z equals 0 plane would be x and y at z equals 0. Okay. So now we are going to represent a point in the rectangular coordinate system. So a point in rectangular coordinate system is located by 3 coordinates, x, y, and z. The point can be reached by moving from the origin the distant x in the x direction, then the distant y in the y direction, and finally the distant z in the z direction. So then, we have a point here. To reach to this point from the origin, we're going to move x1 in the x direction, y1 in the y direction, and z1 in the z direction to get to that point. Here's a practical, a real example. Point Q is located at 3, -1, 2. So from the origin here, we're gonna move 3 in the x direction, -1 in the y direction, and 2 in the z direction. That is point Q located at 3, -1, 2. Another method to define a point is to consider 3 surfaces, namely x equal constant, y equal constant, and z equal constant planes. The common intersection point of these 3 surfaces is the point to be defined, and the constants indicate the coordinate of that point. For example, consider Q. Which is the intersection of 3 planes. The x equal 3 plane here. Here is the x equal 3. That means that plane lies in the y, z. The y equal -1 plane is here. This is the -1. So that plane lies in the x, z. And the z equal 2 plane lies in the xy. So the intersection is right there. And that's your point. Here it is. 3 planes. So the intersection, you have this plane, you have this plane, and you have this plane. Here's their intersection. Base vectors. The base vectors are the unit vectors which are strictly oriented along the directions of the coordinate axis of the given coordinate system. So for Cartesian coordinate system, The three base vectors are unit vectors oriented in X, Y, and Z. So the base vectors for a Cartesian system is the unit vector along the AX, the unit vector along the AY, and the unit vector along the AZ. So here are your unit vectors, which are your base vectors. So any point on the x-axis having coordinates x1, 0, 0 can be represented by a vector joining the origin at this point, and it is denoted x1, ax. So make sure you understand what the base vector is. It's very important, as you will soon see. Okay. Now, this is where I usually have a little fun. What is differentiation?
Sir, that it has to do with time, sir.
Hmm?
It has to do with time.
Time?
Sir, is it finding the rate of change of one thing in regards to the next?
Absolutely. So, and the rate of change is referred to as
What do you mean, sir? The differential?
yeah, the rate of change of one thing with respect to the other is referred to as what?
Are you talking about the gradient?
That's the gradient, right?
Yeah.
So, I have a function y equal let me do. I'm gonna get back my marker.
So you're going to bring your cursor up to the top to bring down the top bar.
Hmm?
You're going to bring your cursor up to the top to make the bar drop back down. So you can select the marker.
No, that me I do, man.
Aren't you because I see your eraser down the bottom?
Hmm?
I see your eraser under the word along. Bring it up some more.
Up some more.
Yeah.
Oh. So y equal x square. What is dy by dx?
Change in y respect to change in x.
And what this work out to?
Sir, 2x.
Oh, you get that?
Sir, because you differentiate the power and you multiply it by the current power, then you minus the power by 1.
So you multiply it by the current power. And you reduce the power by 1. That what you say?
Yes, sir.
So really and truly, how they get that?
You know, I'm not sure, sir. I just always just take it as gospel.
Like we take a lot of other things, right? Which is sad, right?
It's the way of the world more well, sir.
No, we can't. If it not work for us, then we can just say, boy, I saw the world I run. No, I want you to get a little piece of paper. And make a little table. Y x squared. So when y equal 1, what? When x equal 1, what is y?
Sir.
When x equals 1, sir?
Yeah. Actually,
Oh.
actually, I want to So I want you, when x equal 1, what is y?
Sir,
One,
before
okay, sir.
differential or after differential?
I have a function,
The first circle.
y
Oh, one.
equal x squared, without saying anything about differential.
Uh,
Y
one,
equal
sir.
x squared. So if x equal 1, what is y?
1, sir.
Right? So x equal 1, y equal 1. X equal 2,
Y is 4.
is a 4. Three,
9.
4,
16.
all right. Now I want you to make for me a plot. This is x. This is y. So plot these points here. What your graph look like? It looks something like this.
It look more like a 75-degree angle. Look more like a 75-degree angle.
A 75-degree angle. Okay. These are your points. Of course, we left out 0. When x equals 0, y equals 0. Right? So that's our point. When x equal 1, y equal 1. When x equal 2, y equal 4. When x equal 3, y equal 9. And when x equal 4, y equal 16. And when x equal 5, of course, this not draw 2 proper, y would be equal to 25, right? You agree?
Yes, sir.
Okay. Now, for this graph, I want to find the gradient at this point, at some point here. what do I do?
Sir, your friend there.
Rise over
Rise
run.
over run.
At that point, right?
Yes, sir.
Back up, man.
Yeah.
So you draw a tangent at the point. And you would take this rise over this run. Right? Here is your point. Now, let us not put a value on it. To go from y at this point to y at this point, we change by a very small fraction of y, right? And similarly, to go from x at this point to x at this point, we change a very small fraction of x. You agree? Tell me if you agree.
Can you repeat, sir?
I said, to go from y, this is the point that we draw the tangent to. So we draw this tangent. But I'm saying to go from here to here, we make a small change in the value of y, right? And this is the point which has a value x. So to go from here to here, we change a small x. Tell me if you agree or you lost. This is your y
You just
value.
change a small value, sir.
This is your y value. To go from here to here, you make a small change in y. And to go from here to here, you make a small change in x, right?
Yes, sir.
Make sure everybody get that. You're at x, have a certain value here. You draw a tangent here. X have a certain value, y have a certain value. Small change in x and a small change in y bring you to here. In other words, say y was 3. Say y was 4. That means x was 2. If you change x by 0.1, the value of y would be 2.1 squared. Get it or you don't get it?
Yeah, agreed.
You agree?
Oh, you still use the function, sir.
Yeah, because the what you say happen? What you say happen now? Me tank the sketch. Oh boy. So y equal x square. All right. I'm going to save myself the agony of drawing that again. So on that graph, me change x on the graph by a small amount. Go from one point to the next. The small amount I'm going to call delta x. So y would be x, would become x plus delta x square. Like I said, if x was 2 on that graph that this function give me, if I change delta x, x by delta x, y would be x plus delta x squared. No, y plus delta y would be x plus delta x squared. Agree? That's not so hard to understand, man. You agree or you not agree?
Yes, sir.
Yes, sir. I agree.
Everybody agree?
Yes, sir.
Mm,
Expand this for me and tell me what you get.
Sir, x squared plus
X squared
plus
plus
2x delta
delta X
plus
plus
delta x squared delta
delta
x
X square. Everybody agree?
So it might be
Yes,
delta
sir.
squared x squared though.
Huh?
Might be delta squared x squared.
No, man.
All right.
Remember, delta X is a small change in X. So delta X squared, that's good.
All right.
Everybody agree?
Yes, sir.
Yes, sir.
All right. Let me ask you this and think about it. Suppose delta X, remember, we said delta X is a small change in X. So suppose delta X was 0.001. What would be delta X squared?
So 10 to the negative 6 or 0.000001.
All right. So the point is, since delta X is already a small change in X, delta X squared is a smaller number compared to delta X. So for all intent and purposes, we could basically say this almost go to 0. You agree?
Yes, sir.
yeah.
But remember the graph say y equal x squared. So this y, we can cancel with this x squared, right?
Yeah.
Right? Everybody with me?
Yes, sir.
So delta y over delta x, which is the gradient at that point, would be equal to 2x, right? You agree?
Sir,
Hmm?
if you divide both sides by delta x, you would get rid of the delta x, but you have delta y by delta y.
This is delta x.
Yes, sir, that's what I'm.
Oh, shit. So that would be 2x, right? Agreed?
Yes, sir.
Yes, sir.
Yes, sir.
So the gradient at any point on that graph with y equal x squared is 2x. So delta y by delta x is the same calculus we know as dy by dx, eh? Now, when you look at this and at the function, you see that this is n x to the n minus 1, which is this. So when you teach your start teach your calculus, and say dy by dx is n x to the n minus 1. And you don't know how you come by it. And then you come in and my electromagnetics class, don't tell me, say, that's how the world run. You see, when I started learning calculus in high school, this is where we start.
Sir, then save time nowadays, sir.
Eh?
Then save time nowadays and
Yeah, them cheat, you know, because them give them a formula and know where it come from, so not have to rely too much on memory. Which I don't think is good. So this is the basic formula for differentiation. Now, you can imagine now, if you had like y x to the fourth minus 3 x cubed plus six over x square. Now, to go through this with this, it would take you the 4 year, it takes the degree, that's all. Because you'd have y plus delta y would be equal to x plus delta x to the 4th plus 3 times x plus delta x cube plus 6 over x plus delta x square. And then if you go expand it, and if you go drop off or go to 0, that's a nightmare. But since we now know this relationship, it's an easy thing. It just amounts to 4x cubed minus 9x squared plus 6 over x cubed. All because we know what it is all about. I'll go further now and say now, when y equal one function in x multiplied by an next function in x, in the same way like how we develop this, we develop what we call the quotient rule. Is that the one they call the quotient rule or the, well, you have that one is the product rule, right? So if you have y equal this multiplied by our next function.
Yes, sir.
And
Use the
we
product rule.
use,
When it is divided, use the quotient rule.
right. So if we have a function and this divided by our next function, we use the quotient rule. But they all come from this. Right? So now, you know what differentiation is all about. So when we talk about differential elements, right, we will be able to appreciate that. Which I honestly think is injustice. You go to class and they just throw down a number of formula and say, go study that and practice that without having an understanding as to where they come from. All right, so we're gonna do differential elements, but I think I want to stop there today. So we'll pick this up on which day again?
Friday for me, sir.
Eh?
Friday for me.
Next week, Friday, sir.
Yeah, so we'll pick this up at 11 o'clock on Friday.
Yeah, man, sir. Sounds good.
All right. So I'll inform you of the link that I'll be posting different things for you guys. I'll let you know on the chat group before the next class.
All right, sir. Respect.
All right.
But sir, everything good differently? Like you okay?
Yeah, man. Why you ask?
Oh, sir. Let's check your seed.
Oh,
Make sure it's everything good.
yeah, man. Everything good. I think you'll hear something.
No, sir. Something to do for me here, sir.
Yeah, like my brother I drop out, you know.
Yeah.
Well, last month and a half.
Oh, Jano, sir.
And then my house and country burned down.
Oh, Jano.
So I think of them thing that you hear.
No, sir. Me never hear nothing like that.
But me good, me I go on.
Yeah, man, sir. My condolences to your family.
Yeah, man, respect. All right, so take it easy. Next week, Friday.
All right, sir. Take it easy, sir.
Yeah, man.